We present a new approach for multivariate characterization and detection of software performance antipatterns. We work in an open research collaboration environment between universities and industry. Our team is composed of members belonging to Isolab Solutions, Princeton, USA, Ericsson Telecom, and BIT in Karlskrona, Sweden, Gran Sasso Science Institute, L'Aquila, Italy, Free University of Bolzano in Italy, KIT Germany, University of Stuttgart, Germany. Now we have Matteo talk about his part.
Hello everybody. This is Matteo. I'm part of the team at the University of Bolzano. So let me start by briefly introducing the context of this work. So essentially, DevOps is a sensitive matter nowadays, since it is employed by many leading companies to develop large-scale software-intensive systems. And this setting usually requires a tight collaboration between actors, as you can see on the right side of this slide. So we have software developers, architects, test engineers, and so on, tightly collaborating together to perform scalability assessment and take the right decisions along the development lifecycle. So in this context, software performance antipatterns enable a common language to guide scalability, root cause analysis, and refactoring as well. And so the problem here is the lack of efficient approaches for software performance anti-pattern detection. And plus, many existing approaches use predefined threshold on a set of variables that they require a lot of manual work and domain knowledge, and this is often very impractical. So the research gap that we try to fill is the lack of efficient methods to detect the software performance anti-patterns. And we try to develop a method for characterizing and detecting software performance anti-pattern, which is enough computationally efficient to be integrated into continuous integration and continuous deployment and development pipelines. So we started from the following research questions. So first of all, the first question is how to develop an efficient approach to characterize and characterization and detection of software performance anti-patterns. Second one is what is the computational complexity of this approach? And the third one is what is the usefulness in a real world setting? So now I leave the floor to Catia to introduce the software performance anti-patterns.
So hello everyone, I'm Catia Trubiani, and for software performance anti-pattern, we were first of all inspecting the work in the literature. So Connie Smith and Williams, they were collecting a catalog of many anti-patterns, and the specification and the importance of anti-pattern is that collect both the problem and the solution. So some examples of anti-patterns that we were investigating in this paper are, for example, the application hiccups, that is a periodic violation of the baseline requirements, or the empty semi-track transition issue on a large amount of short messages, and so on. If we move at the next slide, we will see that the main characteristics of software performance anti-pattern, they can be differentiated by looking at a specific interval of time, so realizing on a snapshot of a software system, or evaluating a certain amount of transient behavior across the time. As an example, in the first case, there is the blob, in which we have a component that is managing most of the business of the application. And as an example of a transient behavior and analysis of performance indices, we have the traffic jam, by which at a certain point in time, there is a congestion in a certain point that alleviates after a certain amount of time. So starting from the specification of Mitte-Williams, we then provide a logic-based representation that is later used also as part of this work. And I leave the floor to Ricardo to present the overall approach.
I will talk a little bit about the case that we investigate in this research in Ericsson. So basically, we investigated one large real-time telecom system that includes more than 20 subsystems, and the system uses service-oriented architecture. The system is a real-time system, which means it has high performance requirements. And in the specific case of our investigation, the system was expected to handle 16,000 transactions per second. And to give an idea of the scale of the system, it should be able to handle at least 10 million users at the same time, which means it needs to have good enough performance. And then the approach we have developed here is essential to verify the system early on in the development process. We have collected data from, in two different ways. To answer question 1 and question 2, we collected data from a controlled experiment where we ran performance test session, and then we collected this data and prepared to use in the investigation. While at the end, we have conducted a survey with a few colleagues in Ericsson to obtain their opinion in terms of the perceived usefulness of our approach from their respective points of view. And I hand over to Alberto.
We now present our approach to answer research question 1, how to develop an approach to characterize and detect software performance antipatterns that can be integrated into continuous integration, continuous development, and deployment pipelines. We use profiles based on the most likely used scenarios that are employed to define the performance test cases to be run. Scalability requirements are defined based on low load performance test results that support the implementation of automated pass-fail criteria. Performance tests are run using short runs, 30 minutes, and increasing loads. Multivariate analysis of performance testing results generate slope and normalized distance assessment for each service. Services are then classified based on multivariate analysis. We use analytical modeling to provide multivariate analysis of software performance antipatterns. Euclidean distance between modeling and measurement results of the multivariate pair of slope and normalized distance are used to detect software performance antipatterns. We next present the results of XPA characterization and detection using the described methodology. We employed an MG1 queuing system with vacations to characterize software performance antipatterns using the multivariate approach. We parameterized the model using measurements from an Ericsson large telecom system. The figure shows the partition induced in the SPA domain by the multivariate pair. Slope represents the performance degradation as a function of load, which is related to the capacity design of the system. The normalized distance represents the ability of the system to meet performance requirements, which is related to customer satisfaction. In this slide, we present the main results obtained from the application of our multivariate approach at Ericsson. The main contribution of the approach to the state-of-the-art in scalability assessment resides in the automated evaluation of the scalability requirement, which enables automated assessment of what, where, and how of scalability assessment. What represents the pass-fail assessment for each service. Bullet mark services in the left plot were assessed as pass, while X mark services were assessed as failing the scalability requirements. The slope of the linear regression line of test results with different load levels represents scalability degradation. In the figure to the left, we present a risk assessment view of scalability. Normalized distance of the baseline is a surrogate for risk impact, while slope is a surrogate for risk probability of occurrence. Where represents the location of the services impacting scalability. The Haas diagram in the plot at the right of the slide represents a multivariate sort of the scalability assessment for each service using the pair normalized distance and slope. Status updates, resource updates, DB data management, and recompose were identified as the candidates for refactoring. How represent the approach to correct the software performance antipatterns? We use software performance antipatterns as a common language between performance testers, developers, and architects to identify the approach to be used to correct the scalability problem. We map the software performance antipatterns to the pair normalized distance and slope and use Euclidean distance for software performance antipattern detection. In this figure, which is not in the paper, we show the use of k-means clustering approach for the automated detection of software performance antipatterns. In the next slide, we present the k-nearest neighbor classification for the automated detection of software performance antipatterns. In this figure, we show that the k-nearest neighbor classification is able to classify all the services. The research question 2 is the assessment of the computational complexity of the proposed approach. The decomposition approach used, based on parametrization of the analytical model, enables the integration of the approach into continuous integration, continuous deployment pipelines. In this slide, we show the computational complexity of the proposed approach as compared to state-of-the-art heuristics. In the state-of-the-art heuristics, several parameters are used to characterize the SPAs, while in our approach, you use response time derived from a calibrated analytical model. Our approach provides a clear improvement in the computational complexity when compared with state-of-the-art heuristics. It is linear with the length of the data to be processed. The research question 3 is the perceived usefulness of the project team members with using this approach in their system. A survey was conducted among experienced architects, developers, testers, and the project manager that were actively engaged in the project. Most of the performance requirements are set manually in the used software development process. The results indicate that project teams strongly agree that the perceived usefulness of the proposed approach is related to the expected increase in software quality and in the software reliability. Most of the software engineers also expect to see reduced deployment costs and reduced time for software deployment. In summary, the lessons learned from the application of the approach to Ericsson is that there is a high perceived usefulness in applying the following process at Ericsson. First, use automated scalability pass-fail go settings. Second, use an automated approach for identification of the components that represent scalability bottleneck. And third, employ a common language for communication between developers and testers to guide scalability root cause analysis and refactoring. For more information, please contact us at https://isolabsolutions.com. Thank you very much for your attention.